This presentation is about an Internet of Things network coordinated artificial intelligence engine designed to produce loading and delivery schedules for capacitated vehicle routing problems. It represents joint work between Dr. Ashok Murthy from Devices Unlimited Corporation and myself, Ernesto Gutierrez-miravete, affiliated with Rensselaer at Harvard. Let me start by describing a bit the problem, the capacitated vehicle routing problem. It originates as an outgrowth of the well-known old traveling salesman problem, consisting of finding a route for a traveling salesman that has to visit a specific number of customers in the most efficient way. It's an old problem. There has been solved. Different approaches have been used and successfully to solve the problem. Many years later, the traveling salesman problem led to the recognition of an associated problem called the vehicle routing problem. In this problem, one starts with a collection of warehouse goods that are stored in a specific location and are to be distributed to a variety of geographically scattered sites or locations. The objective in this case is to determine the loading scheme, the delivery routes, and the schedule of the vehicles that are going to be used to deliver the goods. More recently, a great deal of interest has been placed on the capacitated vehicle routing problem. The difference between the capacitated vehicle routing problem and the standard vehicle routing problem is that capacity constraints, operational constraints that are very important from a practical standpoint, are incorporated into the problem as restrictions. And therefore, whatever approach is designed to tackle the problem must take into account packing constraints, loading, unloading sequences, axle weight limits, late delivery penalties, plus whatever other constraints that may be involved in the process. Here is a schematic representation of a traveling salesman problem consisting of 100 locations in two-dimensional space. A traveling salesman is going to start from one of those locations, and it's supposed to visit each and every one of those 999 locations without backtracking or repeating visits. The resulting tour, optimal tour, is shown on the right-hand side and is one of the n-1 factorial over 2 possible tours. So you can see that because of the combinatorial optimization nature of this problem, there is a large number of possible tours and only one is the winner in this particular case. Standard optimization approaches have been used to deal with this problem, and many solutions are available and reported in the literature. The vehicle routing problem is a little different. In this case, we have our trucks on the right-hand side that are loaded with goods that are to be delivered to the locations marked in red on the left-hand side. And this is supposed to happen in the most efficient and least costly manner. That is the standard vehicle routing problem. Now, when we add capacity constraints into the vehicle routing problem, we come up with the capacity vehicle routing problem. And this could be all kinds of constraints, as I mentioned before, from the axle weight limit constraints on trucks to road accessibility, to late delivery penalties, to loading, unloading schemes that are most appropriate to facilitate loading and unloading at the destination locations. So those restrictions make the problem more complex. Now let me elaborate about our approach to the capacitated vehicle routing problem. We have created an original hybrid stochastic simulation genetic algorithm method to tackle the capacitated vehicle routing problem. In our approach, we are easily able to account for loading, unloading constraints, axle weight limitations, and delivery delay penalty constraints that can be incorporated for all the delivery vehicles considered in our problem. Moreover, all the packages or pallets to be delivered can have different weight, different characteristics, and these can be incorporated into the analysis. The use of stochastic simulation is effective for us because through it and through the use of random numbers, we can create a statistically representative number of loading schemes. When we couple a genetic algorithm to this stochastic simulation algorithm, then we will generate optimal or near optimal tour for each of the stochastically simulated loading algorithms. And we'll do this subject to the specified constraints of the problem: axle weight limitations, loading, unloading, late delivery penalties, etc. Each replication of the combined algorithm produces a near optimal tour, optimal or near optimal tour. Now, since we use stochastic simulation, we're going to produce multiple replications, and because we create these replications, we end up with a distribution or optimal or near optimal tour. We have embedded our combined hybrid stochastic simulation genetic algorithm into a computer program that we call Gator, which is ready to be used in practical applications. And I will show one example to demonstrate this. Here is a schematic representation of what's happening inside our Gator program. We start with the input on the upper right, which consists of characteristics about the packages to be delivered, as well as characteristics of the delivery vehicles, and of course, the destinations to where the packages are to be delivered. Once this input is incorporated into the program, stochastic simulation using random numbers creates random loading for all the trucks in the fleet. Therefore, the genetic algorithm takes the assigned random loadings on the fleet of trucks and carries out genetic computation in order to produce optimal tours for the trucks in the fleet, given the specific random truck loading created by the simulation approach. Because we're interested in creating multiple replicas of such scenario, we repeat the process, create a new random truck loading, pass it through the genetic algorithm, and every time that we do that, we come up with a near optimal or optimal or near optimal truck routing for our fleet, given the specifics of the loading scheme assigned by the simulation modeling part of the code. Here is the look of the interface of our Gator program. As you can see in the middle, we have on the left-hand side information about the pallets, right? Characteristics of the pallets. Each pallet has a unique identifier. And of course, we have the characteristics of the delivery destinations. All these were obtained, the delivery destinations were obtained from a public database of addresses, and the pallet IDs and characteristics were created through simulation modeling. We have buttons that enable us to activate late delivery penalties. We decide how many trucks in the fleet, how many pallets, and then we just simply click load the trucks, load the pallets, and we are going, and we can compute a situation fairly quickly. Here is an application example that I use for demonstration. We have deliveries scheduled into 3 main hubs: Northwest, Center, and Northeast part of the United States. And the details are as follows. We have a total of 200 pallets. We have simulated the pallets having different weights, assuming a Bible distribution of weights. We assume a total of 150 delivery locations. There will be 6 vehicles carrying out the deliveries. And we also account for late delivery penalties through a logistic function that will rise the cost rapidly if the deadline is missed. The mileage cost is specified, and the axle weight limits are computed using a standard approach. Now, when we plot the results of computation, 200 replications of our algorithm, we look only at the cost, the mileage cost associated with these 200 tours. We get a distribution, we get a spectrum. We have costs ranging from about 29,000 to 32,000 monetary units, and we have a characteristic tri-model distribution. When we include the late delivery penalties in the cost, besides the mileage cost, we get this distribution, which is a smoothed out distribution, with a range, again, between 29,000 and 34,000 monetary units, and a center around 31,000 monetary units. As you can see, there is plenty of choices there. All these 200 tours are near optimal tours, so there's plenty of choice for a designer or decision maker that needs to make a selection of what's the best course of action for this delivery of these pallets to the 150 locations using the 6 trucks to choose from. Now, let me elaborate a little bit. Here is a representation of the tours carried out for 2 of the trucks in our set of 6. And it's clear that these 2 trucks actually carried out complete transcontinental tours. They went through all 3 locations. At the same time, with the same collection of results, we found that there were 2 of the trucks in one of the replications. 2 of the trucks only had packages that had to go only as far as the center of the country. So it started from the Northwest, and then they didn't have to go all the way to the East Coast. So depending on how the loading is assigned, since the loading is assigned by stochastic simulation, we can easily identify those loadings that result in tours in which at least 1 or 2 of the trucks, or maybe more, end up traveling in a more restricted route, and therefore resulting in lower mileage costs. So there are plenty of possibilities. We have run a number of simulated instances like this, and I believe we are ready to run more elaborate cases involving more complex type situations and different geographic locations. So in conclusion, I think we can make the claim that we have created and developed a hybrid simulation genetic algorithm that can be used very effectively for the determination of optimal or near optimal solutions to capacitative vehicle routing problems. We have found through computer experiments that the algorithm is robust, stable, and is capable of producing these near optimal, optimal, or near optimal solutions in a rapid and efficient manner, minutes to get results like the ones I just showed. And the resulting near optimal routes constitute an assortment of alternative potential delivery routes that provide flexibility to decision makers that are charged with the responsibility of coordinating the deliveries of goods to locations. And with that, I'm going to bring my presentation to a close.